This is your presenter Asloob Mudassar, and I am presenting slide number 65 of the course on laser physics. Question is, in addition to the detail covered in question number 64 about the energy levels in a molecule, give further detail about the energy levels. Also discuss the level occupancy at thermal equilibrium. The answer is, consider a diatomic molecule consisting of two identical atoms. Three types of motions are possible in a molecule: electronic, vibrational, and rotational. Vibrations and rotations occur on a much slower time scale than electronic motion. If the molecule is excited electronically involving electronic motion, the electrons occupy larger orbits, as a result of which the minimum of the potential energy curve corresponding to the excited state is shifted to larger value of R, where R is the internuclear separation between the two atoms. The ground and the first excited states are shown in figure 65.1. For small oscillations about R0, the curve corresponding to the ground state can be approximated by a parabola. So let me first of all describe equation number 65.1. This is equation number 65.1, and this is over here the ground state of the molecule. You see that R0 is the distance. This R0, we have plotted the nuclear separation or the internuclear separation between the two atoms on the horizontal axis, and we have plotted the potential energy of the molecule along the vertical axis as a function of R. And you see that the ground state has been labeled as 1 over here. This is the electronic ground state, and this curve, which is a parabolic curve, is actually contains the potential energy curve, contains many vibrational levels, and the vibrational quantum number for the ground state is V double prime. So it starts V double prime is equal to 0, then V double prime is equal to 1, then 2, then 3 and 4, and then so on. And we have labeled the last level as P and P prime, which we shall describe in the text. So R0 is the separation at the distance when the molecule or when the two atoms within the molecule is at a separation R0, then they have the minimum potential energy. And you see that when it has a minimum potential energy, it is not equal to 0, but it has some value which is equal to half h nu naught. The separation between these levels, that is between the vibrational levels, between two consecutive levels, is h nu naught. But the lowest vibrational level in the ground electronic state has an energy not equal to 0, but has an energy equal to half h nu naught. So this is the ground state configuration that we have shown. But when the molecule gets excited, the electronic state is shifted, which we call as to the level 2. This level 2, which we have labeled as level 2, this is actually the first excited state, or more precisely the first excited electronic state of the molecule. So you see that when the molecule is excited, then the nuclear separation between the two atoms also increase. So you can notice a shift in the curve of the vibrational parabolic curve is shifted to larger value of distance r, because the separation between the atoms is not then equal to R0, but equal to some value greater than R0 when the molecule is excited. So we have a curve which is equal to this curve when the molecule is in the first electronic excited state. So for that there are also many vibrational levels that we have shown. The vibrational quantum number is now V single prime. So V single prime is equal to 0, and then equal to 1, then equal to 2, and so on. So the vibrational levels will increase. So you see that up to the 4 levels, we can say that the separation between the vibrational levels is the same up to the level 4. But if you go beyond the level 5 and so on, which we have not shown, the separation between the levels would decrease. That is, the separation between the two consecutive vibration levels would decrease along with the increase in vibrational quantum number. So V prime is the vibrational quantum number for the first excited state, and V double prime is the vibrational quantum number for the ground state of the molecule. And the more significant point is that when the molecule is excited to the first electronic state, then of course the vibrational curve and is shifted to larger value of the internuclear separation. Let me read the caption of this figure. Potential energy curves corresponding to the ground and the first excited states. So we have shown the potential energy curve of the molecule for the ground state and also for the excited state. And for the first excited state, there you can notice a shift towards greater value of R in the potential energy curve of the first excited state in comparison with the ground state of the molecule. So I think that all the features have been explained. Okay, so for small oscillations about the value R0, the curve corresponding to the ground state can be approximated by a parabola. So you see that if the molecule is undergoing small oscillations around the value R0, small oscillations, not very large, so it means that you are that is a few vibrational levels could be occupied, then you see that you can treat this curve as a parabola. So I think that up to the diagram that I have shown, that up to the level 4 or 5 the curve is fairly symmetric about the axis. If you pass the axis perpendicularly through the value R0, then you see that the curve is fairly symmetric, and we may record this curve as a fairly parabolic curve. But for larger values of the vibration about the distance about the value R0, the molecule is not following the parabolic approximations. So parabolic approximations will only be valid when the molecule is oscillating about the value R0 and the amplitude of oscillations is not significant. Okay, the restoring force between the atoms will be elastic, being proportional to the displacement from the equilibrium, that is the displacement from the value R0, because R0 is the equilibrium distance, is the distance where the molecules gets at the equilibrium position. So when there are vibrational oscillations, the restoring force between the atoms will be elastic, being proportional to the displacement from equilibrium. The vibrational energy levels will be spaced equally, and the energy gap between the consecutive levels will be given by. So this delta E V, V stands for the vibrational quantum number. So the change delta E is the change in two consecutive vibrational quantum numbers is equal to h nu naught, and that is equal to h bar multiplied by the square root of k naught over mu, where k naught is the elastic force constant and equals the curvature of the parabolic curve. And mu is the mass that we have explained earlier, and that is mu is given by m1 into m2 divided by m1 plus m2, where m1 and m2 are the masses of the two atoms respectively. When vibrational motion of the molecule is taken into account, the vibrational levels corresponding to each electronic state are designated by 1, 2, 3, 4 and so on. So you see that in each electronic state, that is for the ground state of the molecule and for the first excited state of the molecules, the vibrational levels have been labeled as 0, 1, 2, 3, 4 and so on for in both cases. Under the parabolic approximation, the energy levels are similar to those given by harmonic oscillator and are equally spaced. Otherwise, the spacing between the levels would increase as the vibrational quantum number increases, which is evident in the vibrational levels beyond V prime is equal to 4 in the first excited electronic state. But you see that we have not plotted the vibrational levels corresponding to quantum number V prime is equal to 5, V prime is equal to 6 and so on, because the spacing between them will decrease as if you go with the increased value of the vibrational quantum number V prime. But we have not shown those ones. We have only shown those levels which satisfy the parabolic conditions, in which the curve is quite symmetric about the minimum of the curve and the parabolic approximation is valid. But you see that for higher levels, for the first excited states, the beyond the value of quantum number 5, the separation between the levels will keep on decreasing as the principal quantum number value is increased. So such levels are not do not fall under the approximations of the parabola, and so we cannot treat them as a harmonic oscillator. The potential energy curve shown in equation number 65.1 correspond to the case of a fixed internuclear distance, and thus are not a true representation of the energy of the molecule, as the atoms are never at a fixed distance. So you see that here, for example, in the ground state we have shown that R naught is the fixed distance. That is when there are no vibrational, that is in the ground state, the separation, the internuclear separation between the two atoms is fixed to the distance R naught. But in reality, this distance is also slightly varying for the atoms, for the separation between the atoms. V double prime is equal to 0 does not coincide with the minimum of the curve while the atom is in the ground state, because of the 0 point energy equal to half h nu naught. So you see that for the ground state, V double prime is equal to 0 does not correspond to the minimum of the curve, but it has got some value, and that value is equal to half of the value of the separation between other levels. That is, it is equal to half h nu naught. And this half h nu naught is referred to as the 0 point energy, which is equal to half h nu naught. The same energy as we find in case of the harmonic oscillator. Okay, in the V double prime is equal to 5 vibrational levels of the ground state, that is the vibrational levels of the ground state corresponding to V double prime is equal to 5 are oscillates between the values P and P prime. So I have shown P and P prime, so this level corresponds to V double prime is equal to 5, and the molecule will oscillate between P and P prime. That is, sometimes the separation between the molecules will decrease to the point P, and sometimes it will increase to the point P prime. So the separation, the internuclear separation between the two atoms in the molecule will oscillate about the value R naught. So it will oscillate up to the point P and then to the point P prime, and the oscillations will keep on going. These 2 points lie on the curve where the vibrational energy is entirely equal to the potential energy, and thus the kinetic energy is 0. A molecule can also possess rotational motion and thus possesses quantized rotational energy. For a linear rigid diatomic or a linear triatomic molecule, the rotational energy is given by ER. R stands for the rotational and E stands for the energy. ER is the rotational energy of a molecule, that is equal to B times into J plus 1, as shown in equation number 65.2, where capital J is the rotational quantum number. You see that here we have the vibrational quantum number represented by V double prime for the ground state and V1 prime for the single state, for the first excited electronic state. But you see that here we are showing that capital J is the rotational quantum number, where B is the rotational constant equal to h bar square over 2I, where capital I is the moment of inertia about an axis perpendicular to the internuclear separation between the center of masses. Therefore, the total energy possessed by a molecule can be written as total energy of a molecule, of a diatomic molecule, is equal to the energy due to electronic state plus due to the vibrations of the molecule plus due to the rotation of the molecule. And we can simply write that the total energy is equal to electronic plus vibrational plus rotational. Rotational energy levels are specified between the vibrational levels, that is between two vibrational levels many rotational levels can exist. So let me show. You see that these are the horizontal bars within the curve, within the potential energy curve are the vibrational levels, and between two consecutive vibrational levels there could exist many rotational levels. So rotational levels are specified between the vibrational levels. Rotational energy level in two consecutive vibrational levels of the ground state along with possible transitions are shown in equation number in figure 65.2. For example, this figure. So let me explain this figure first. Caption of the figure is a transition between rotational levels of two consecutive vibrational levels of ground electronic state of a diatomic molecule. First of all, we are talking about the ground electronic state of a diatomic molecule, and second is that we are considering two vibrational levels. So you see that the two vibrational levels are the lower vibration levels, the lower vibration level is V double prime is equal to 0, and the upper vibration level and the next vibration level is V double prime is equal to 1. So V double prime is equal to 0 and V double prime is equal to 1 are the two vibrational levels of the ground electronic state of the molecule. So you see that I have also shown these two levels over vibrational levels over here. V double prime is equal to 0 level, V double prime is equal to 1 level by single lines. But you know that I have shown over here as many lines because these are the rotational levels corresponding to each vibration level. For example, V is equal to double prime is equal to 0. You can notice that there are many vibrational levels. And again corresponding to the vibration level V double prime is equal to 0, you can notice many vibrational levels, and I have labeled these vibrational levels with quantum numbers J0 for the corresponding to the vibration level V double prime is equal to 0. So J0 is the rotational quantum number, and similarly J1 is the rotational quantum number corresponding to the vibration level 1. Similarly, for higher vibration levels, we can change the subscript. That is, we can change the subscript from J0 to J1 to J2 to J3 and so on, corresponding to the increased value of the vibrational quantum numbers. So here we are considering two vibrational levels, and each vibrational levels has been shown to be split into 5 rotational levels. So we have J is equal to 0, 1, 2, 3, 4, 5 rotational levels in the vibration level V double prime is equal to 0, and similarly we have shown 5 rotational levels for the vibration level V double prime is equal to 1, and those 5 rotational levels have been labeled as J1 is equal to 0, 1, 2, 3, 4 and 5. Up to 5 levels have been shown. And you will notice one thing, that the spacing between the rotational levels would increase as you go with a higher value of J. For example, J is equal to 0 and 1 has a rotational separation which is increased from J is equal to J0 is equal to 1 to J0 is equal to 2. Similarly, from J0 is equal to 2 to J0 is equal to 3, this separation is increasing, and similarly this separation also increases for the rotational levels shown for the next vibration level, which is V double prime is equal to 1. So you see that now there could be a transition from rotational level to rotational levels. That is, there is a transition between the rotational levels of the vibrational level V double prime is equal to 1 and the rotational levels of the vibrational level V double prime is equal to 0. Two transitions have been shown labeled as P branch and R branch. For the P branch, so let me read the text so that we can further understand. The transitions belonging to the R branch correspond to delta J is equal to plus 1, whereas the transition in the P branch correspond to delta J is equal to minus 1. So the P branch, in the P branch we have delta J corresponding to minus 1, that is the 3. For example, the rotation level 3 for J1 is equal to 3, for example, is decaying to J1 is equal to 4, for example. So 4 will decay to 5, etc. But you see that for the R branch, delta J is equal to plus 1, that is the level 5, J1 is equal to 5, J1 is equal to 5 will decay to J0 is equal to 4. So under that condition, the delta J is equal to plus 1. So the transition belonging to R branch corresponds to delta J is equal to plus 1. Delta J is equal to, you see that the upper value of J minus the lower value of J. Whereas the transition in the P branch corresponds to delta J is equal to minus 1. that is delta j. You know that delta j is equal to j1 minus j naught, some value of j1 minus the lower value of minus the higher value of j naught. Spacing between the consecutive rotational levels is not constant but increases linearly with the quantum number j. That is, so this is the what we have given the relationship of the energy between the two consecutive rotational levels. That is the ER of j, that is the rotational energy for quantum number j minus rotational energy at quantum number j minus 1 is equal to 2 times b into j. So this is, you see that the this gives you the energy difference between the two rotational levels. Okay, so what we are going to discuss next is that next we describe the level occupancy at thermal equilibrium. Let us designate capital N as a function of EE, EV and ER as the population contained in the rotational and vibrational levels of a given electronic state. At thermal equilibrium, we can write that N is directly proportional to GE, GV, GR, and also multiplied along with that is e to the power minus the total energy of the molecule EE plus EV plus ER divided by KT. So this is the proportionality is due to that we are assuming thermal equilibrium, and the population under thermal equilibrium follows this rule. So this is given in equation number 65.3, where GE, GV and GR are the degeneracies of the levels corresponding to EE, EV and ER energies respectively. You see that we have also discussed what are degeneracies in one of the previous slides. So if you are concerned to know about further details about the degeneracies, so you should consult one of the previous slides. Thermal equilibrium attained at room temperature means that the diatomic molecule will lie in the lowest vibrational level of ground electronic state. In polyatomic molecules, the spacing between the vibrational levels is much smaller than kT, and many excited vibrational levels of the ground electronic state may then have a significant population. Using equation number 65.2, which is this equation, and the relationship in equation number 65.3, the probability of occupation of a given rotational level of the lowest vibrational state can be written as. So you see that we have written down the probability of occupancy of the rotational level J. So what is the probability that our rotational level J is occupied? This is given by this relationship shown in equation number 65.4, that is P of J is proportional to 2J plus 1 times e to the power minus B into J plus 1 divided by KT, where 2J plus 1 is the degeneracy of the rotational levels. Using B is equal to 0.5 centimeter inverse, T is equal to 300 Kelvin. The plot of P of J versus J is shown in figure 65.3. Due to the factor 2J plus 1, the most heavily populated level is not the ground rotational level J is equal to 0, but the one whose rotational quantum number J satisfies the relationship. And the relationship is 2J plus 1 with a subscript M is equal to the square root of 2KT divided by B. So this will give you the probability of occupying the level J, and here you can see the plot of this probability also. So let me read the caption of figure 65.3. Population distribution of occupying a rotational quantum state J of a given vibrational state. So you see that we have plotted the quantum number J of the rotational quantum number j along the horizontal axis, and we have plotted the probability of occupying the level rotational level j along the vertical axis. You will see that with increase in quantum number j, the probability of occupancy will increase and will reach at some value around the value of j close to 15, and you see that beyond that one the probability will fall, and ultimately it will reach to 0 for higher values of quantum number j, for higher values of rotational quantum number j beyond the value of 40. So this is a typical curve. You can notice this curve that for a lower value of j it is not maximum, but it is maximum for some value of j, for example in this particular case around the value of 15. So beyond the value of that 15, the probability of occupancy of the rotational level j will decrease. So you see that we have explained what we have explained. We have explained in further detail the electronic state, the vibrational levels in that state, the vibrational levels, and then the rotational levels corresponding to vibrational states. Then we have talked about the occupancy of these states at thermal equilibrium. And then we have also plotted the possibility or the probability of occupancy of the rotational state G, and we have given its plot also. So this answers all the queries in the question. So this is the end of slide number 65.